Yeah, let's just start.
Welcome back. So now we have the fourth and last lecture of Lance Dixon.
All right, thanks a lot, Matthias. And in this lecture, I would like to do a few things, which is sort of just tell you a little bit about the complexity of loop amplitudes in QCD. I won't say too much about that. And then we will do an example of a complete cross-section calculation, mostly, of the simplest hadron collider process, which is Drell-Yan production in PP collisions. And we'll go through that somewhat. And then I'll make a few comments about why these QCD corrections tend to be so big, things like that. So this is just to review the general anatomy of these higher order corrections, which we already went through before. You want to do a leading order cross-section. All you need to do is square up some tree amplitudes and do some integral over their phase space. And next to leading order, we need one loop amplitudes. And we also need to have tree level amplitudes, including the radiation of one additional parton into the final state. For example, QQ bar goes to a Z plus a gluon, or Q bar G goes to Z plus a Q bar. And we'll encounter later on divergences in the phase space integrals that will be up to 1 over epsilon and even 1 over epsilon squared that will cancel against virtual divergences on the other side. And at next to leading order, there are also intricate cancellations across all three categories. The two-loop amplitudes, or contributions to the doubly virtual cross-section for the same kinematics as at tree level, and as well as virtual real contributions and double real contributions. And these are actually state-of-the-art in terms of developing methods for them that can be done efficiently enough to be able to handle more complicated processes than this. So the virtual corrections, we'll start with just the result for the very simplest one. This integral, this amplitude here, where you exchange a gluon between a QQ bar line. You can also call this essentially a form factor, and this is the one-loop form factor for quark production from a virtual photon. And this is the same graph that Eric showed earlier, except he was considering different kinematics in the end. He was doing the anomalous magnetic moment of the electron. And there you want to be in the limit that the electron mass is very large compared to the photon momentum. Whereas in this case, we're interested in the limit where the virtual photon is very energetic compared to the mass of the quarks, which we're going to, in fact, set to 0. So in that limit, the amplitude is divergent in the infrared, and it has a overlap between virtual soft and virtual collinear divergences, each one of which produces a 1 over epsilon squared. In fact, all the worst divergences are contained in the scalar integral with the same kinematics, which is has a form. I'm not going to put all the factors in, but when you Feynman parameterize it with, I'll call the Feynman parameters A1, A2, and A3. It has a form which is if I got it right, something like this. So this is an easy integral to do. And when you do it, you'll discover after the right Wick rotation to get a sign, a minus 1 over epsilon squared contribution, which essentially accounts for that leading term. But then there are some other terms where you have to take into account the Feynman diagram numerators to get the 1 over epsilon term and the constant terms. There's also an issue of what scheme you do your calculations in that affects things at the finite order. You can consider a scheme where the number of degrees of freedom of virtual gluons is continued as you continue the number of dimensions from d minus, gluon being transverse might have d minus 2 degrees of freedom, where d is 4 minus epsilon. That corresponds to setting delta r equals 1. And that's called a conventional dimensional regularization scheme. And that was the most widely used scheme for a while in calculations. The 't-Hooft-Veltman scheme, it still assigns the same number of degrees of freedom to unobserved gluons, but external gluon states, which we don't have any of here, would be treated differently using fixed helicities. And that's a lot more convenient these days. Also, though, there are other schemes where you can set delta r equals 0, and that's at one loop, that would be like a dimensional reduction scheme or something we call 4-dimensional helicity, and that has some advantages in terms of supersymmetry. Ward identities are maintained in that scheme. But the most conventional thing to do for QCD is to set it to 1 and work in the CDR or 't-Hooft-Veltman scheme. Anyway, after you evaluate that, you get this simple result here. Now, of course, there are more complicated one-loop amplitudes. A while back, we looked at like 5 gluon scattering, and we found some simple configurations, and then about a page worth of functions which aren't even defined here, but they're made out of dilogarithms. And then we got 16 pages, and then we decided it was about time to stop doing analytic stuff and go numerical. This was the case. Just making one of these partons into something that was massive, like a WZ or a virtual photon, led to a large explosion in complexity of the calculations. But nevertheless, you can evaluate these formulas, and you can also construct numerical versions of loop amplitudes with many legs that allow you to get a lot of next to leading order cross sections out if you can handle the phase space integrals. And we'll get back to the phase space integrals in a second, but I just wanted to say a couple words about two-loop integrals, partly to make contact with Johannes's talk. So Johannes derived a lot of beautiful results for things that were not multiple polylogs or Goncharov polylogs, but involved elliptic polylogarithms. And he mentioned that a application of that was to the sunset integral, shown here. And so this integral was studied for quite a while, and then started to be connected to the elliptic polylog story in about 2013. And one of the places where this integral plays a role, where this momentum is generic, I guess in Johannes' notation this was S, p squared was equal to S, and these equal masses, is in top quark production. So in top quark production, there are various types of graphs, but this graph in particular is closely related to the sunset integral. As Eric mentioned, you can perform integration by parts on generic types of integrals, and if you do it in loop momentum space, you will find what we call boundary terms. Remember, in the generic integration by parts, you will have propagators here, these 7 propagators raised to different integer powers. And the general structure of the integration by parts identities is to move you around in the space of the integers ni that Eric was describing. So you have these 1 over these 1 over inverse propagators to the ni. And the IBP equations change these ni's, and occasionally an ni will go to 0, which is a boundary term, and because that propagator has vanished, it corresponds to a graph that's obtained by just xing out that propagator and bringing the two vertices on either side towards each other. So you see, if you take and do that 4 times and are able to remove these gluon propagators, then you are left. So now I'm contracting these guys to a point, and I'm remembering that the momentum flowing in here is now going to be the sum of the top quark momentum and the gluon momentum. So it's going to be not on shell for the top quark, because there's an additional injection of momentum here. So there will be some generic invariant S or p squared here, and these masses are all the same. So that's precisely the sunset integral. So this integral ends up being a source term for some differential equation for this integral. And so essentially, you need these elliptic polylogs from the sunset, and then you need to do more integrals on them somehow in order to produce this integral. Now, in fact, back about 7 years ago, these integrals were done numerically. And it was possible to get away with this. Numerical integration can be very slow, but if you have a simple enough phase space, and in top quark production, you basically have just 2 variables. It's a 2 goes to 2 scattering. So you have st and u, and also the mass m squared. But s plus t plus u is related to m squared, so you can remove u. And then you can divide s and t by m squared. So you basically have two variables. So you can make a grid in a 2-dimensional plane, calculate the amplitude through some slow numerical technique, and then fit to the grid and evaluate it faster using an approximation from interpolation between different points. So that's what was done in the case of top quark production. And here's the theory for top quark production that results from these virtual corrections, as well as very sophisticated real radiation. And you can see there's a certain uncertainty band from the scales, but it fits pretty well with the data from Atlas and CMS. This is pretty old. By now, there's data at 13 TeV as well. Now, of course, if you want to do something like top production with 1 extra gluon, with 1 extra jet, then you will need integrals like this, but ones that have 5 external particles instead of 4. So how many variables will those depend on? If this one depends on 2. 5, yeah, exactly. So then trying to make a grid in a 5-dimensional space is a much bigger challenge. And so there's plenty of room for analytic understandings that will help in going further to more complicated processes. Any questions about that? In the case of other processes which have 2 goes to 2, we're in a more fortunate situation. For example, this integral here is one of the most complicated ones that appears in the production of 2 W bosons. There's also maybe some non-planar ones as well, but those integrals all belong to a class of these multiple polylogs, or G functions, and a lot of advances in understanding those functions, together with advances on the real radiation and making the one-loop amplitudes numerically stable, made it possible to compute a large class of 2 goes to 2 processes at next to leading order. So there was a real flurry of activity around 2013 to 2017. Over here, if you look at all these processes here, they're all various versions of things we call 2 goes to 1. So you have a production of a single W or Z or Higgs boson that was done around 2003. This says W Higgs, but it really is a virtual W that splits into a W and a Higgs. So it's extremely similar to just W or Z production. And then these calculations were redone in a more differential way. But then over here, you started to get to two-body processes like diphoton, Higgs plus jet, the TT bar process I mentioned earlier, Z plus photon, jet-jet, ZZ, WW, et cetera, et cetera. So all this was sort of made possible by alleviating a bottleneck in these 2 goes to 2 virtual integrals. The technology was there on the real side to handle real radiation in this case. But since then, things have slowed a bit more in the sense that 2 goes to 3 is in principle possible, but there's only been one 2 goes to 3 process so far done somewhat to completion. So that's sort of the status for NNLO up through 2 goes to 2. Now I want to step back and go back to the simplest hadron collider process that can be described perturbatively, which is Drell-Yan production, and walk you through some of the next leading order calculation. First, though, let's talk about the leading order kinematics. So we take and we first compute a leading order partonic cross-section. I'm not going to go through that in detail because we're going to do something similar at the next order. But the formula you get when you sum over the square of the 4-point amplitude, which we computed before, and I should have also said you have to integrate over the angles of the electron and positron, you get a standard formula which looks very much like the E plus E minus to mu pair cross-section you might have also seen in your field theory courses. It has this famous 4 pi alpha squared over 3. It has a term proportional to the electric charge of the quark squared, and it has a 1 over n color that comes into the color averaging in this case. In final state color, you typically get factors of NC, but for initial state color, you end up getting a 1 over NC. So that can be translated into a differential cross-section in the mass, which involves this commonly defined sigma 0, which has a 1 over m squared in it, and then this prefactor, where we usually keep the quark charge out of it. And it has a delta function in that the partonic center of mass energy, S hat, has to be exactly equal to the mass squared of the lepton pair. When we insert that into the general formula for the QCD improved parton model, we multiply it by the relevant parton distributions, which is a quark on one side and an anti-quark on the other side, plus the opposite possibility. And then we get a delta function in S hat, which is, remember, S hat was S times the 2 momentum fractions, x1 and x2. And then we have to do this integral here. And we can do an integral, if we define tau to be m squared over s, then this is tau times s, and we can pull out a factor of s, except I screwed up, and this s should actually be in the denominator. Sorry about that, because when you pull it out of the delta function, it goes in the opposite direction. Okay, but you get this constraint. So what you are sensitive to is the product of parton distributions that have the product of whose x's is equal to a fixed value tau. This is often called a parton luminosity function, whereas a parton distribution depends on one flavor, quark, antiquark, or gluon. A luminosity function depends on a pair of flavors because it's a convolution of the two. But you'll sometimes see those because they're very useful to estimate how many events you're going to get in a certain class. So anyway, you get these products here. And you have to integrate over x1 and x2. Of course, you can't go down to arbitrarily low x1 because x2 can never get bigger than 1. So there's some range of integration that's cut off by the fact that these parton distributions stop at x equals 1. Now there's another thing you can do in Drell-Yan. Well, there are actually multiple things you can do, but the next simplest thing you can do is look at the distribution of the vector boson in rapidity. Remember, rapidity was this longitudinal variable that involves the energy in the pp center of mass frame and the z component of the momentum of the vector boson. And to construct something that has good boost properties along the z-axis, this combination E plus pz gets multiplied by a factor, which is something like gamma 1 plus beta. And this one gets multiplied by the same factor, gamma 1 minus beta. So anyway, there's just this thing has a nice shift under boosts along the z-axis. So let's rewrite this equation by taking, multiplying by 2 and exponentiating it. So we get e to the 2y over here. And on this side, we get just the ratio of E plus PZ over E minus PZ. We can rewrite that. These are the energies in the center of mass frame as just P2 dot PZ. It's the momentum of the Z dotted into P2 in one case because it's going along the minus direction. So it measures E plus PZ, and P1 is going along the plus direction, so it measures E minus PZ up to some overall factor, which is equal in the two cases. But you can rewrite that. P2 is the momentum of the Q bar over X2, and P1 is PQ. This was PQ bar. And these two are actually equal to each other because in the Z center of mass, the quark and anti-quark have exactly the same energy. And that's what you pick out with these dot products. So in other words, this combination of the rapidity is just x1 over x2. So we have two equations and two unknowns. We know that x1 times x2 is related to the invariant mass, or to tau, by this equation. And we know that x1 over x2 is related to e to the 2y. So it's easy to solve those equations for x1 and x2. In other words, when you measure the rapidity of a Drell-Yan pair and its invariant mass, at leading order, you know what the momentum fractions were of the two partons that produced it. So one of them is square root of tau e to the plus y, and the other is square root of tau e to the minus y. Of course, in higher order corrections, that's not true, and you have to generally do a fit of the data to a formula that involves the probability of additional radiation that smears the relation between these two kinematic variables. But roughly speaking, if you can look at Drell-Yan production that is far forward, where the rapidity is large positive, then this x1 gets very large, and this x2 gets very small. And when you have central rapidity, it's most often from equal values of x. And so by looking at the distribution, you can sweep out you can measure different parts of the parton distributions in convolution or in products. Any questions about that? Okay, now we're going to do the next to leading order corrections. In order to do that, we start with one of the real radiative processes, because I already gave you the formula for the virtual correction, so that one's basically there in the bag. And we take this 5-point process, and we had labeled these particles as 1 and 2, and these as 3, 4, and 5. And we did the sum over helicities earlier, or at least I did it in the 4-point case, but it's very similar in the 5-point case, because you remember that the helicity amplitudes always had a spinor product that had either a 1 or a 2, and then through the Fiertz identity it had either a 3 or a 5 on the other side. And using these parity symmetries, we get all 4 combinations with equal weight. So this formula is very intuitive from the point of view of those single helicity amplitudes. And it has denominators which are going to control the structure of the integration over the phase space. There's an S12, that's going to be fixed to the mass of the Drell-Yan pair, so that's not going to do much. But S34 and S45 are going to become singular in soft and collinear limits. Now, to simplify our life, we're not going to consider arbitrary angles in the decay of the virtual photon to the electron-positron pair, but we're going to integrate over those angles just to reduce the dependence on various variables. So we can actually just do an integral over that angle, and when we do that integral over the angle of k1 mu, k1 nu, we get this formula here. And this formula is easy to derive from 2 different constraints. One constraint is that if we take eta mu nu and contract it with k1 mu, k1 nu, well, that's just k1 squared, but this is 0. And on the other hand, it's minus S12 over 12 times eta mu nu, eta mu mu, which is just 4, plus k12 squared over 3, and this is S12 also. So you see the relative coefficient there is dictated by this constraint, that these are 0. And then to get the overall normalization, you can just set mu equals 0 and nu equals 0. And then you're doing the integral of E1 squared times the angular average of 1. And this is in the center. You could do this in the center of mass frame for K1 plus K2, in which case E1 is 1/2 of the sum of E1 and E2 squared, which appears on the other side. And when you impose this constraint, you'll find that you get this overall normalization. Any questions about that? So that's also equal to the angular averaging of the other momentum K2. So up here we have, the reason we wanted this identity is because we have S13 times S13. So that's K1 mu, K1 nu contracted with K3 mu, K3 nu. So when we contract this with a couple of K3s, only this term survives, and it becomes S13 plus S23 squared. And the other terms work similarly. 2 of them are equivalent. The 1 squared, this one and this one, give that term. These 2 guys give this term. Okay, so now we've reduced things so that the only variables that we have to worry about integrating over are S34, S45, and S35. And now we'll just trade. So we really have only a 2-dimensional phase space. There's some azimuthal angle that doesn't matter. And for that phase space, we could work now in the 3-5 center of mass, where there's an energy E4 of the gluon, and then some angle of the gluon with respect to the 3-5 incoming beam axis. But it's a little simpler if we trade for some variables that run between 0 and 1. So this variable is always used for 2 goes to 1 processes. It's the ratio of the invariant mass divided by the partonic center of mass energy. So that quantity is inevitably called Z, and it can be can run up to 1. It's 1 when this energy goes to 0. And the Born process and the virtual corrections are all concentrated with the delta function at Z equals 1. But in this radiative process, Z is less than 1 because because this invariant mass here is a little bit bigger than the lepton pair in invariant mass. And in principle, it can go down near 0 if you have a very high energy collider. And then there's a second variable, y, which is a proxy for cosine theta, just adjusted to run between 0 when theta is 0 and 1 when theta is pi. And then if you use this parameterization and plug in for what E4 is, well, E4 is the dot product of the momentum K4 with the center of mass momentum, because in the center of mass frame, it just points in the time direction, so it picks off this energy, but you have to normalize it properly. So you get a formula like this. And you can also rewrite it using momentum conservation in terms of S12. In any case, when you plug in these formulas, you find that E4 is more or less a proxy for, or is equivalent to 1 minus Z up to some overall scaling factor. So it doesn't have any theta dependence. And the theta dependence is carried through, in the formula, through S34 and S45, which you can work out to be related to the overall S35 by these factors of y times 1 minus e and 1 minus y, 1 minus e. So in the collinear limits where y goes to 0 and 1, one or the other of these will vanish. In the soft limit where z goes to 1, both of these will vanish. Any questions about that? So when you plug these formulas in to this expression, you get, for example, S34 plus S35 gives you this gives you 1 minus 1 for the S35, and then a minus y, 1 minus e for the S45. So you get this quantity squared, and then you get a similar factor involving 1 minus y for the other half of the formula. So we just have this function and similar things for the denominator factors. So you just get this dependence on y and z. There's also a phase space measure, which is flat in d cosine theta, and it has a particular dependence on the energy of the gluon. And we need to do the phase space integration in d dimensions, in 4 minus 2 epsilon dimensions, because it's going to have infrared singularities from the corners of the integration. When you make these substitutions in, the phase space measure collapses to something that's almost flat in y and z up to some epsilon dependent contributions. Okay, so now it just becomes a simple integration problem. First, we're going to do the y integration. And in the y integration, you see that there's a 1 over y singularity. That's a collinear singularity because z is so far generic. Z equals 1 was the soft limit, so this is a pure collinear singularity as y goes to 0. And there's another one at y goes to 1. So we could call it a hard collinear divergence. It's been separated as long as z is not equal to 1 from the soft divergence. And when we do the integral, well, we can separate the two by partial fractions, and they're related by symmetry. So up to a factor of 2, we just need to look at the first term multiplying this numerator. So we can, in order to treat it, we realize that if we expand the 1 over y term multiplying the singular factor y to the minus 1 minus epsilon, if we expand it in y, then anytime we pick up a y here, we can immediately set epsilon to 0. And we might also want to expand the term in this contribution as well, although this term, as y goes to 0, vanishes, so it doesn't actually give a contribution. And then we do the integral over y, and we get a minus 1 over epsilon factor and a 1 plus z squared. And then we have this prefactor here, and we can expand this further in epsilon. There were some of these color prefactors and so on. Putting them back in, here's that singular term with a 1 plus z squared in it and a 1 over 1 minus z from here. And that might look familiar to people who remember the PQQ leading order splitting kernel. And then there's some more contributions from expanding things out past the 1 over epsilon pole that show up here. So this piece here is going to be absorbed in a second into a renormalization of the quark distribution functions. So the parton distributions we were working with in the lowest order calculation were actually sort of bare distribution functions. Remember, these distribution functions are equivalent to operators through the Mellin transform, the infinite set of operators labeled by the spin or Mellin moment n. And those are composite operators, so they need to be renormalized, and they have anomalous dimensions. And in the renormalization process, you have these 1 over epsilons, and you have to pick a scheme for renormalizing them. And as usual in dimensional regularization, the conventional scheme is to do a modified minimal subtraction. So you subtract the 1 over epsilon pole, but also certain finite parts, including logs of 4 pi and Euler-Mascheroni constants, just like you do for coupling renormalization. But because you're really renormalizing an infinite set of operators, you get the subtraction involves a convolution type of integral. And so it actually appears with some z dependence. But it involves the lowest order kernel. And that is why we see this factor of 1 plus z squared over 1 minus z again. There's another term in renormalizing this distribution that comes from initial state gluons. But we don't see that in this particular channel. It comes up in another channel. This is a surviving correction of the cross-section, and this is the right answer. This piece here, well, I swindled you a little bit. In order to make life easy, I calculated the real radiative corrections in a helicity scheme, whereas the standard approach is to use conventional dimensional regularization. So if you redo the whole thing by summing over all the polarizations, in particular the gluon polarization, without using helicities, but with using full d minus 2 states, you get a contribution that exactly cancels this. But you get the basic sense of this formula from this calculation. So this is the correction that comes from the real radiation. It's not quite true. There's another term for the real radiation, which has a delta of 1 minus z and a plus 1 over epsilon squared. That one cancels the divergent part, also the plus 1 over epsilon, cancels the divergent part of the virtual distribution at the virtual amplitude interfered with the Born, which sits exactly at delta 1 minus z. And so this is the Born term, the lowest order correct contribution. And then the next to leading term, the piece that we've been computing, is dq for the quark anti-quark channel. And it depends on z and on the factorization scale. There was a factor in the measure of the factorization scale which ended up over here in a logarithm with m. And we also got a contribution at delta 1 minus z, which came from the constant part, the finite part of the virtual correction. So this is basically the final textbook form that you see. Notice that it's a singular distribution as z goes to 1. So there's a regularization that's required, as we talked about last time, when you have any kind of a 1 minus z plus in the denominator. You define it on a test function. In this case, we have an extra log 1 minus z in the numerator. So it's defined by subtracting whatever you're multiplying it by, evaluated at 1. There is also a correction that can be derived from this subprocess, which is the same matrix element, but of course it's crossed around, and that leads to this formula. Now, notice that this formula has no 1 minus z plus singularity in it. That's a soft gluon singularity. Here we have only a quark in the final state. So when you combine those two terms, you get a correction to the total cross-section, which is very large at the LHC. Now what I'm showing you here on the left is leading order, next to leading order, and also next to leading order, and not just for the total cross-section, but for the rapidity distribution, which one can calculate through similar techniques, and by just not doing that integral over y, but freezing it in the right way. So the thing to notice is that you get a very large correction to both the rapidity distribution and to the total cross-section, which is just the integral of this curve. And we also did the calculation at next to leading order, and we found that the cross-section seemed to come back down again. And we had very small uncertainties on when we varied the renormalization and factorization scales by a small amount. But very recently, this total cross-section, so the integral here, was evaluated at one more order, n cubed LO, by Claude Dour, whose name you've heard repeatedly in Johannes's lectures, and Falco Dulat, who is now doing self-driving cars at Waymo. So they were convinced by this curve. No, anyway, and Bernard Misselberger, who is coming to SLAC in April. And they did it at one higher order, and they found something that was kind of surprising. And what you should do to compare these, first of all, so far they just did Drell-Yan. That means a virtual photon only and no Z boson. However, the dominant corrections are most likely very similar between the Z case and the virtual photon case, the enhancements to the cross-section. And so they found that the NNLO result, which should roughly be represented by this, the error band here does not include the result at one higher order. Now, those of us who've been doing this game are very used to leading order results getting shifted well outside their error band, but it's kind of surprising and annoying that an NNLO result could be shifted outside of its band here. So you're supposed to look at 100 and see that maybe there's a shift. Now, a lot of other things changed between here and here, so you can't completely compare them. For example, this NNLO result lies near the top of the NLO band, whereas here it's near the bottom. And it may have something to do with how the parton distributions were treated in going from one to the other. But the bottom line is, these scale-dependent bands that people produce, like us, should be treated with a grain of salt. They, especially if they're narrower than you thought they had any right to be. So you can actually see that this NNLO band is wider over here. It kind of narrows down here, so you might worry that that was accidental, and this kind of confirms it. Now, of course, this n cubed LO one gets rather narrow right here, so one could ask the same question at the next order. Any questions about that? Yep, Alex?
Piece that are dependent on the scheme, the FTH versus
Yeah.
CDR, one of the contributions. But did it end up canceling by the end of your calculation?
Yeah, so the thing is that the PDF evolution is really defined in the CDR type scheme. So you should really switch to CDR to do it. Now you might say, does that mean that all helicity amplitudes are useless? Because they really correspond to a Tuff-Veltman scheme. Could be FDH. Safer to go to a Tuff-Veltman. But you can't really convert a helicity amplitude to the CDR scheme, because the CDR scheme requires you to sum over all helicities, including epsilonic helicities when you're in d dimensions. But there's a way to convert between the two. In other words, if you write, there's a way to write the total cross-section at one loop in terms of the tree cross-section times a particular divergent factor. For example, Catani gave a formula for this. If you evaluate that formula twice, once in FD8, once in a Tuff-Veltman and once in CDR, the difference, the finite leftover, is the same. So you can basically convert your formula to CDR in that way. There's a universal shift.
Is it known to all of this?
No.
Just to a couple?
It's known to N and LO. I don't know if it's known to N cubed LO. I mean, so for example, we calculated the basic 2 goes to 2 parton scattering at 2 loops using helicity amplitudes. They were also calculated slightly before us by Nigel Glover, Maria Elena Tejeda-Yeomans, Babis Anastasio. And then we sat down and compared results for the total cross-section. And you know, even at 1 over epsilon squared or cubed, they won't be the same if you take them literally. But if you write them in terms of these universal factors, then the finite remainders agree for a Tuff-Veltman scheme. So in practice, you can use that to convert. It could probably be worked out at n cubed LO by now. I'm not sure, but anyway, it hasn't really been necessary to do that yet because nobody's done a complete calculation of an n cubed LO process this way. Done it other ways. Any other questions? It is archive number 2001. That's 2020. You guys haven't been reading the archive recently. It's from January. It's actually very recent, not very old. Any other questions? So this approach I showed you for Drell-Yan to do all the integrals analytically, nobody does that for complex processes, because also the experimentalists don't want to just know the distribution in invariant mass, because they have to apply cuts on the individual leptons. So they have to put in theta functions on the lepton kinematics. So you're not allowed to do those integrals. And in general, they have very complicated sets of cuts. So you really want to do as much of the calculation numerically as possible for the phase space integrations, where the experimental cuts play a role. So there's two strategies to try to automate next leading order calculations that takes into account the fact that, well, there are 1 over epsilon squared poles, so you can't very easily do the numerical integration right away. You first have to expose the poles. So the two solutions are called slicing and subtraction. And so here's a picture of the phase space integration that we did in the Drell-Yan case, just to guide your eye. You remember we had S34 and S45. There was also S35, but it had to sum up to S1. But there was a constraint on the sum of S34 and S45. So anyway, in this region here, that's the collinear region when 3 is parallel to 4. S34 goes to 0. Over here, S45 goes to 0. And then there's an overlap when both of them are small, which is the soft wide angle region. Or it could be soft collinear if it's on this edge. But we can always define a small S min that controls this strip. If we require that all of the partonic invariant masses are are larger than a given amount, then we will remove all of the singular regions. So we can easily do a numerical integration, and we don't have to worry. We can do it straight in 4 dimensions over this blue part. The only problem is we need to know what these integrals are too. So there is a way to use the factorization of the amplitudes in this region to perform the integral there approximately. And this is one version of it. If you want to go to very general processes, there are perhaps other variables that are better. There's some variable called n-jettiness, which at least one of you worked on as a summer project. And it can be used as a way of separating the singular regions from the non-singular regions in any type of event. And furthermore, the factorization of the processes is understood through resummation in n-jettiness to high orders. And so you can use that to work out the analytic behavior on this n-jettiness parameter that is analogous to the S min here. And you can get analytic dependence of the cross-section on that. And then you have to do the rest of the integral numerically and check that numerically that it cancels powers of logarithms in that regulation parameter, and then you're left over with a constant. Now sometimes this is computationally rather difficult if you have to see large logarithms and also the final output doesn't have them in it. So there's another method, general method. These all have various variations. But the other general approach is to do subtraction. In a subtraction method, you find a function that mimics the behavior of the cross-section in all singular regions, and then you subtract it. And then the remaining thing after you've subtracted it can be integrated over the entire phase space because you've canceled the singularity. And then you would like to be able to integrate the subtraction terms, ideally analytically, but if you can do it numerically at each power in 1 over epsilon, that's okay too. So I think this is probably, I've been going for almost an hour. You want to take a quick break? Okay, let's take a 5-minute break, and then I'll finish up later. Okay?